So I'm Ryan. I think everybody, and I know most people who registered today. Um, Pleased to be joined by Sarah Maleska, who's helping to co-host and facilitate the meeting. We were just chatting. This is actually our 26th Builder Breakfast session that we've been hosting either in person or online as part of the local community of the city's transition to performance-based codes, and to support all of our builder, architect, designer community with the latest and greatest in green building technology, design, construction practices for high performance houses. So we're happy to have everybody join us. And um, we had intended to do this one at Anvil or in person, but we will be doing that this fall. So we will get back to serving breakfast along with the great content and speakers that we have. So stay tuned for when we announce our fall session sometime probably in September. We'll let people know. We'll have a save the date kind of thing that happens. Do you want to? Maybe we can. I think we should probably proceed, Sarah. Does that sound good?
Yeah, I think so. The waiting room slowed down, so let's get her going.
Perfect. All right. Do you want to? I can. Do you want me to
Oh,
handle the
this
land
is
acknowledgement?
me. Sorry, I was
Okay.
pressing mute, unmute, and it wasn't working.
You're all good.
Um, Hi everyone, Sarah Maleska on the Climate Action Team. It's great to be here today with all of you. And I'd just like to start off with a land acknowledgement that we recognize and respect that New Westminster is on the unceded and unsurrendered land of the Halkomelem speaking peoples. We acknowledge that colonialism has made invisible their histories and connections to the land. And as a city, we are learning and building relationships with the people whose lands we are on.
So just a few housekeeping stuff with Sarah. So we're webinars recorded. Make sure to identify yourself, remain muted. Both speakers, I think, Mark, you and Ben, happy to take questions throughout and during the presentation. So just put them in the chat box or raise your hand. Ben is going to present on, so we've got the keynote with Ben on electrical load strategies. Mark Rudehauser is going to be presenting from the electric utility, talking about electrical connections and policies and advanced metering and things like that, as well as we're going to want to facilitate lots of conversation and discussion. Sarah's got an update on city activities with Climate Action Group, and then Sue and I are just going to chat a bit about some Energy Save New West updates. We've got a case study, and we want to promote the embodied carbon pilot that we have ongoing, and recruit some of you folks with projects to participate in that. So that's our agenda. And then we'll start off with our keynote. So we're really pleased to have Ben Gaducci here. Ben's a professional engineer. He's also director with a company called Riverside Energy Systems that specializes in renewable energy out of Kamloops. Funny enough, I've indirectly known Ben because he's been doing stuff on renewables, and my organization's been doing stuff on HVAC design, but we've never officially collaborated like this before. So really happy to have Ben here. He is an industry leader in solar PV and storage, as well as electrical design and with zero energy buildings, and been heavily involved in renewable system design, installation, and training with building professionals such as today's session for over 16 years. Prior to Riverside Energy Systems, Ben also worked with BC Hydro for 12 years in power systems design, and he's been teaching too. So he's got quite a few hats that he wears as well with Thompson Rivers, and most recently with BCIT as a part-time faculty member with their zero energy buildings program. So doing the renewables course there. So super pleased to have Ben here. He's got an awesome presentation on electrical load strategies in new construction and renovations. And with that, I will mute myself and turn it over to you, Ben.
Thank you, Ryan. Just make sure I share my screen properly here. There, does that look right? Are you seeing
Oh,
my projection?
you're on the presenter mode. Close. You had it the first time.
How's that?
You're golden.
Nice. Okay, well, thank you for inviting me to be here today. My only regret is that I haven't had a chance to meet any of you in the group that are attending today to hear more about the projects you're working on and how I could have maybe tailored my presentation to meet your needs a little better. But I'm hoping that you'll find the information useful, and it'll give us a chance to potentially connect offline later on. So I'm going to be talking sort of a high-level overview of electrical design considerations for Part 9 building electrification. And this is a lot of fun stuff. Now, before we get into that, I'll just say a little bit maybe about Riverside. As Ryan was mentioning, we are solar PV and storage experts. We are available for consulting, feasibility work, advising, engineering, design, and installation. We do a lot of work with grid-connected, off-grid, and microgrid type systems. And we have done a tremendous amount of work with Solar Ready, Net Zero, and most recently Living Building Challenge design. So we work all over BC, and we're certainly available to help. We've been around since about 1995, and we're based out of Kamloops. I'm noticing my slides seem to want to change all by themselves, so that'll hurry me along, I guess. So this is basically the overview of what I want to talk about, why electrical design matters for Part 9, and then some of the electrification challenges we face that can get us into trouble if we don't think about things in advance. Techniques for limiting the demand on a home's electrical service, which I like to talk about as ways to modify the home's electrical personality. We're looking at different techniques for that. I want to talk about how solar and storage impacts the electrical design mix. Conventionally, solar and storage are often left as afterthoughts, and this can result in very problematic issues, not the least of which will be the outcomes are not what the builder or the homeowner may have intended. And we'll look at some case studies. So I'm going to look at, in some detail, a contemplated energy retrofit using both classic sizing methods and another method that isn't talked about much called demonstrated load. And then we'll look at a zero energy build that included solar and storage, and how all these design techniques wrap together to give us good outcomes in that project. And then lastly, talk a bit about how we're going to achieve good results in this sandbox that we're playing in. So why does electrical design matter for Part 9? I mean, traditionally, we haven't been as careful about electrical design in Part 9 buildings as we have, in other ventures. However, it turns out that electrification can dramatically affect electrical service sizing, and that can be super costly if we do unnecessary upgrades. And it can be even more costly if the utility needs to upgrade their infrastructure to accommodate us. If we think about electrical service sizing and demand mitigation early on, project outcomes can be much improved. And of course, solar and storage also significantly affect the electrical design of the building. And if we don't consider those up front, we can wind up painting ourselves into a corner. And it turns out that some of the same things that are driving electrification are driving solar and storage as well. They have like a synergistic effect with each other. So when we electrify, I mean, as we all know, HRVs and domestic electric hot water, heat pump technologies, EV chargers, and the like, it all boils down to higher service demand. And often electrical contractors will advise that the service size needs to be increased. And sometimes that is required. And sometimes if we look at it more closely, we can mitigate that need. So we'll look at that more today. Similarly, with solar PV and storage, the intention is that solar and storage will help us reduce grid energy purchase, help us maybe back up essential loads during outages, and possibly leverage time of use rates. And that's all great, except that they impact the electrical design very significantly, and they have to be thought of upfront. And secondly, solar and storage are not an all or nothing decision. A lot of people think you'd only do solar if it was going to be a net zero home with a net zero energy outcome. In fact, the best business case would be to install some solar versus going all the way to net zero. And that's a topic for another presentation another day. Bottom line is that we should not leave solar and storage as afterthoughts, because if we do, we're risking painting ourselves into a corner and limiting what might be possible later on. So around customer service constraints, as many of you will know, utility services are either overhead or underground. When we're dealing with overhead equipment, service upgrades will usually mean upsizing the service conductors, potentially replacing meter bases, which tends to be fairly straightforward if it's overhead. If the service is underground, then all bets are off. There can be digging, jackhammering, disruption of landscaping, and the costs can be considerably higher. So I'd like to think that if we're going to go to these efforts, we want to make sure they're necessary at the design stage. Another concern is utility infrastructure limitations. If everybody in a neighborhood decided they needed 200 amp or 400 amp services, very quickly transformer and secondary conductors and distribution feeders would begin to reach their capacity limits, and we could even have impacts all the way back to the substation and potentially need substation upgrades depending how extensive the upgrading needs to be in various subdivisions. So not only are we impacting homeowners when we prescribe a service upgrade, we're potentially impacting utilities as well. And electrification across the country is revealing limitations in utility build. And I don't think perhaps that the city of New West is having this problem as much as other utilities might be, but there's parts of Canada, certainly parts of BC, where electrical utilities simply could not give everybody a maximal service size without significant infrastructure upbuilding or upgrading. So a summary of electrical code service sizing requirements, like what are the things that an electrician or an electrical designer would be having to consider when they're sizing a service for a new build or for a retrofit? Well, there's basically three principles. The first one is that we have to base that service size on load calculation. We can't base it on the choice of a main breaker. So we can't just say, all right, we're going to make do with 100 amp service. We're going to install a 100 amp service panel with a 100 amp main breaker. And if we connect too much load, that breaker will trip and we're going to be okay. Well, that might be safe, but it's not acceptable to code authorities. The service size has to be based on load calculations. Secondly, there's this concept of a basic load, which basically your load is never less than this. And that's based on a living area. So it's number of square meters of living area, and we have no control over that. And then the third concept is heavy loads, anything bigger than 1,500 watts. We're allowed to derate some of these, but fundamentally we have to assume they're all going to run concurrently, all at the same time. And so this assumption that all these loads are concurrent very quickly eats up the electrical service capacity. Now, thankfully, there are some permissible load control methods that can limit how big the service needs to be. And we're going to talk about those in a few minutes. Now, first, some terminology that is super confusing. When we talk about the size of an electrical service, what we're talking about is the size of the service conductors that the utility has provided for delivery of electricity to our building. And so the service conductors will be sized and the main breaker will be sized based on the service capacity. So if it's a 100 amp service, those conductors are rated to carry 100 amps 24 hours a day. And the main circuit breaker will be rated to trip at 100 amps. That's what service size is about. So panel size or panel rating are sometimes confused and interchanged with the service size. And there's something very different. The panel rating is really the maximum size of the main breaker or main fuse that we're allowed to use to protect that panel. So if it's a 200 amp panel, we have to protect it with a 200 amp breaker or a 200 amp fuse maximum, and nothing bigger than that. And when we talk about panel size, usually an electrician will interpret that as the number of circuits in the panel. And neither the panel rating nor the panel size really has much to do with the service size. It's possible to have service conductors that are heavy enough for 200 amps, but then only install a 200 or a 100 amp panel with a 100 amp main breaker and load the service to a maximum of 100 amps if that's acceptable for loads. And then the last thing, which is even more confusing, is the rating of the buses or lugs. Those are the metal parts inside the panel that the breakers connect to. And so we'll say a little more about that later, but here's an example: a 200 amp panel with a 200 amp main breaker with 42 single pole circuit space and 225 amp bus ratings. Okay, that would be the full description of a panel. So just a little bit on the terms, just so we're all meaning the same thing as we carry on through here. Now, what's interesting is on the utility side, things are sized very differently. Utilities use engineering standards that are based on empirical operating evidence. And so they ask themselves, what is the likely maximum load versus what is the worst possible case, the Murphy's Law loading. Utilities assume that loads will not all run concurrently. This is called load diversity. And observation of electrical load behavior shows that in fact loads are diverse. And so utilities use this concept, and they're not required to follow electrical code design practices. They have their own engineering standards. They're exempt from electrical code. So here's an example of a pad-mounted underground transformer. It's actually just across the street from my house where I live in Kamloops. This is a 50 kVA transformer, and so it's rated at full load to be able to deliver 208 amps. Well, in my area, which happens to be a BC Hydro jurisdiction, that transformer would commonly be connected to 8 or 10 homes that each have 100 amp service. So inside this red box where electrical code applies, electrical code would say that we have to design assuming for 800 amps of concurrent load because there's 8 100 amp services connected. The utility says, well, no way. If we did that, we'd go bankrupt. We're gonna serve those 8 homes with a transformer that can only do 208 amps. And you might ask, well, why aren't these transformers blowing up left and right? Well, it's because the loads are in fact diverse and they're not all concurrent. So it's a different paradigm. It's sort of a practical empirical approach by the utility versus an abundance of caution in the electrical code. Unfortunately, for electrical contractors and designers designing a building, we have to conform and comply with electrical code, where the delineation is basically at the meter base, and anything behind the meter has to conform to CEC. So, as I said earlier, we cannot justify our service size just based on the size of the breaker. So in this case, we do our load calculation. If it comes out to 195 amps, a 200 amp service is okay. If it came out to 205 amps calculated, our electrician would say, well, you need a 400 amp service or a 320 amp service, which has recently become available in parts of BC. We can't just rely on this 200 amp breaker to trip should we ever get to that 205 amps. That's not allowed. So that's the first point. Can't depend on the main breaker. We have to do service load calculation. It's got nothing to do with main breaker size. And then the living area thing. So this is actually our case study home we're going to look at earlier. It had 2,375 square feet of living space, which using code tells us that we have to assume a basic load of 29.2 amps, effectively that it's never going to be less than that. And so we've only got 70.8 amps left to work with on our 100 amp service. And then thirdly, our continuous loads, which is anything bigger than 1,500 amps, like space heating, air conditioning, electric dryers, ranges, etc. We have to assume that those are all running concurrently. Now, we're allowed to derate some of these a little bit, but fundamentally, we have to assume concurrence, and they add up pretty quickly. So I was going to show you a Burnaby case study home here. So this is a home in Burnaby that we looked at about a year ago, and the homeowner was contemplating an energy retrofit. They have an existing 100 amp service with a natural gas furnace, natural gas domestic hot water, natural gas cooktop, and an electric oven and electric dryer. And when we run the code rules we just described a moment ago, you can see that the 100 amp service is just fine as it is. Now, we'll say more about this in a minute once we look at what their contemplated retrofit was going to be. So
Ben,
yes.
Ben, sorry, just to jump in before we get into the case study example, our friend Austin at Enercan actually had a question here. Specifically around some of the rules where he said, if the 8 homes were 200 amp instead of 100 amp, what would the requirements be on the transformer?
Great question. That'll vary by utility. My experience, hi Austin, by the way, it's good to hear from you. My experience would be that'd be probably a 75 kVA transformer. They'd upsize it by 50%, but it'll depend on the utilities. I think maximum it would be 100, but more likely it would be 75 kVA.
Perfect. Thanks, Ben.
Yep.
There's no other ones, so we can push on.
Okay, you bet. So techniques for load limiting or changing the home's electrical personality. Well, the first one is careful equipment sizing and selection. So, you know, my friend Ryan is much more of an expert on heat pumps than I am. I'm just sort of an electrical guy. But sort of at the HVAC design level, for instance, we can see here that, you know, a standard heat pump versus one with variable refrigerant flow versus cold climate, that the efficiencies at low temperatures are quite significant. So significantly different. So for example, if we take the red curve with a cold climate heat pump down to -13, which I think is -25 or so Celsius, we still have 75% or 80% or so. Maybe is that 75? I guess it's 75% of its efficiency or heating capacity. So if we assume a coefficient of performance of say roughly 2, you know, we're still 1.5 times better than electric baseboards. And so people like Ryan and other heat pump experts might suggest that for the lower mainland, that a cold climate heat pump would be a good choice for this very reason, because it would limit our need for electric supplemental heat, which will, you know, reduce the load on the electrical service. Alternately, we could retain natural gas as supplemental heat if we really were compelled to use a heat pump with a lesser low temperature efficiency. Now there's allowable load demand limiting techniques in Section 8 of the code, aside from where it prescribes how to do load calcs. For instance, Rule 8106, Part 11, gives us control strategies where, for instance, with an EV charger, if we use a controller that's measuring the service current to enable or disable the charger to prevent service overload, we don't even have to count the EV charger in our service calculation. This is a huge benefit. So another one is 8106 parts 2 and 3, which basically speak to something called interlocking, which basically says that if multiple loads can share a circuit, provided we interlock them or use controls so that only one of them can operate at a time, if we do that, then only the largest of those loads needs to be considered. So this is the interlocking concept. And then a super powerful one for retrofits is demonstrated load. So this is a technique where we can look at historical load measurements to justify what the historical service demand has actually been. So in other words, we actually measure how much capacity remains in the service rather than speculating it based on rules of thumb. And so we'll talk about this technique in a moment. So load limiting. So this is an example of a smart load switch that monitors the demand currents on your main panel, and it enables or disables the EV charger. It only enables the EV charger if it could operate without overloading the service. So this is huge. Doing this allows us to completely ignore the EV charger load, which can make a big difference in a service calculation. Load limiting with smart splitters. This is a form of interlocking where we use a device that is powered by a single circuit, which we can connect two loads to, and it prioritizes the loads. In this case, it's giving the electric dryer priority over the EV charger, which means that the EV charger couldn't operate unless the dryer was not operating. If we do this, then we only have to consider the larger of the two loads in our service calc. Big benefit again. Another more sophisticated example of interlocking is using smart panels, which are able to selectively enable and disable various circuits using programming, depending on what the total load is. Now, these are very popular in the US, where electrical code allows them to be used for this purpose. In Canada, they're not widely endorsed yet, although I hear there's been a recent crack in the armor. Apparently, Ontario electrical safety authorities have started accepting smart panels for this purpose, so that's cause for celebration, and I'm hoping that it won't be too long before we'll see something happen in BC around the same thing. Now, this demonstrated load idea, again, this is in code. It's Rule 8106, Section 9. And it basically says that we can use historical load measurements to justify how much capacity we have left in our service if we're wanting to do a retrofit. So we can gather this data in a couple of ways. It's got to be done by a qualified professional. So that would usually be like a master electrician, electrical field service representative, as they're called in BC. Electrical contractors, they're also called, or an electrical engineer, using 12 months worth of data. And that data can be gleaned either from the utility, where the utility makes that data available. So it's hourly data for 12 months, or if you've got time, you could install a third-party power energy data logger of your own and log the data for a month and justify it that way. But the key point here is the measurement intervals have to be an hour or less. Now, I know that talking to Mark yesterday, that New West has their AMI program in progress, and I believe that sometime in the fall that the smart meter program may be fully complete. And the city might want to look at making or planning for this type of data availability for utility customers in the future. It's certainly available from BC Hydro. I believe Fortis BC makes it available in their electrical jurisdictions, and a lot of utilities in Ontario make it available as well. So the way it works, say if it was BC Hydro, you can log into your BC Hydro My Hydro site. You can ask for a data export, and then you request hourly intervals for a full year, and the data downloads as a CSV file, which you can analyze in Excel. So for our Burnaby case study home, we looked at 1 year's worth of data, and we discovered their peak load was 5 kilowatts, and it looks like it happened in the late parts of October. And that peak current, corresponding peak current, was about 20.9 amps. So, earlier we'd looked at that number, using the surface, the living area of the house, and we had found it to be 20.9. So it was somewhat bigger. So essentially, what we're finding is that our measured demonstrated load was less than a third, less than 35% of what we'd calculated it to be using the traditional code methods. And our basic load was only 5 or 6 amps versus the 29 amps that we'd predicted using the living area method. So you can see that there's nothing like measuring it. The measurements show that the projections calculated were not all that close to real life. Now, of course, this will vary with occupant habits and so on, but having demonstrated how the home behaves with those occupants with real measurements, we can now take those numbers and use them. So we'll show that in a moment here. So if we go to the Burnaby case study home, if we'd said, okay, we'd like to do a 3-ton heat pump retrofit, and we're going to use a garden variety heat pump that's not that great at cold temperatures, so we're going to need a 10 kilowatt electric boost, and we use traditional service sizing without demonstrated load calculations, we're going to end up needing to upgrade the service. We're going to need 125 amp service unless we dig a little deeper and go back to the drawing board using just classic electrical code methods. So let's have a closer look. Just by choice of equipment, like say we'd engaged Ryan, and Ryan said, well, hey, why don't you use a cold climate heat pump so you don't need any supplemental electric boost? Well, now all of a sudden we're golden. The 100 amp service suffices just by choosing different equipment. So we could thank Ryan for that one if he was giving us that advice. Or, for instance, so then that would give us capacity to go further. So we could say, well, look, if we still have some capacity left here we have more than 25 amps left in our service, if we use a cold climate heat pump, that gives us the possibility of upgrading our hot water tank to electric. So if we do that, look, we're still good with 100 amp service. So all of a sudden we have options that weren't possible before if we didn't dig deeper with better equipment choice. Now, how could demonstrated load help us? Well, in BC, what Technical Safety BC has said is we can calculate an augmented load from our demonstrated load measurement by simply multiplying it by 125%. So we take our maximum load measured, multiply it by 125% for good measure, a little bit of extra safety, and doing that, that Burnaby, sorry, I got Kamloops here. It's actually Burnaby. That comes out to 26.1 amps as a augmented load calculation. So we take that number 26.1, and we now find that not only could we put in a cold climate heat pump, but for good measure, we could add the 10 kilowatts of boost heat, which would mean it would work even in Kamloops or colder climate zones, and also do the electric hot water tank. And we're still okay with the 100 amp service. So this is a powerful technique in jurisdictions where that data is available. Of course, you can see pretty clearly that we don't have this option if it's a new build. If it's a new build, we don't have any demonstrated load to measure. So we have to use some of the other tricks like interlocking and careful equipment selections to mitigate our service demand impacts of electrification. How are we doing for time, Ryan?
I think we're okay, Ben.
Okay.
You've got how many slides left?
I'm about 3/4 of the way through.
Yeah, you're good.
Yeah.
Go for it.
Okay. So we've talked about the electrification impacts, what happens when we try to electrify all of our HVAC and domestic hot water and that sort of stuff. That affects electrical design. The other thing that really affects electrical design is solar and storage. And the two go hand in hand because as people electrify and their consumption is going to go up, they become more concerned about their energy consumption and resilience during grid outages. And all of a sudden, they're more interested in solar and storage. And so electrification and solar and storage go hand in hand. And because they both really impact the electrical design of the building, I believe that they should all be considered at the design stage. Service sizing and solar and storage impacts considered at the design stage. So simple PV systems that don't have storage will interact with the grid in the way that the solar array and inverter will produce electrical power behind the meter, which generates in parallel with the grid connection, and it will reduce how much energy has to come in from the grid. And at points where it's producing more than what the loads require, energy outflows to the grid. And under the net metering program, that energy outflow is tracked as energy storage that you can consume later. So in effect, the grid acts as a battery. Now, the thing to remember here is that a system like this shuts down when the grid goes down. It doesn't give us any backup. Now, if I remember correctly, the City of New Westminster's net metering program allows up to 50 kilowatts of solar inverter capacity. So New West does have a net metering program. Now, when we add solar and storage to the mix, or add storage to the mix, then more interesting things happen. Not only is the solar system able to reduce our grid consumption and store energy to the grid in the case of surplus production, it also can interact with the grid to leverage time of use rates. Now, BC Hydro has an optional time of use rate now. I don't know whether New West will ever go in that direction, but with time of use rates in place, we can use battery storage to reduce our consumption during times of the day when grid energy is the most expensive. But perhaps just as importantly is this concept that a hybrid inverter with storage will allow us to back up. I'm sorry, my slides are changing all by themselves here. It's like the thing has a mind of its own. I'm sorry, something's gone wrong with my presentation. Just give me a second, please.
You're all good, Ben. Take your time. You got lots of time.
Okay. Okay, one of my slides has disappeared. What I'm going to do here is stop sharing for a moment. And I'm going to have to open it up again. So just give me a sec. This is what software engineering has done for us. I hope there's no software engineers in the group.
Also, it's not really a webinar unless there's one little presentation hiccup. That's what makes it official, Ben. So we're all good.
Yeah, okay. Do I have the right screen up, or is they backwards again?
Yeah, backwards. You'll be good in one more click.
There you go.
We're golden.
Excellent. Okay, sorry for that disturbance.
I think someone commented, nice fish. Maybe your background.
Oh yeah,
Your
yeah.
desktop.
Yeah, I'd love to tell you where that lake is, but I'd have to kill you all if I did. So okay, here we are. So yeah, so what I was getting at is once we have storage in the mix, not only can the solar system interact with the grid to reduce energy consumption and potentially leverage time of use rates, it's also able to back up. So you can see in this architecture, we have a backup panel in which we would connect all of the essential loads that we want to back up during an outage. And during an outage, the backup panel isolates from the grid, and the solar and storage can continue to run those essential loads. So this can be a benefit if we're looking for grid resilience. And there's parts of BC where many clients are concerned about this, particularly, if they're in a wildfire area or zones that are subject to flooding during atmospheric rains and such. So why do we need to worry about this at the design stage? Well, it turns out that electrical service panels are not created equally. So here on the right, I've got two different 200 amp panels. One, I won't tell you which companies they're made by because I don't want to slander anybody, but they're two different 200 amp panels. They both satisfy 200 amp service requirements in terms of load. But it turns out that when we're connecting another source of generation to the panel, it's not just powered by the grid, it's now also powered by solar, that we have to be worried about overloading the buses, the bus bars. Remember we talked about the bus bars early in the presentation? So it turns out that the panel on the left, which only has 200 amp buses, that only accommodate up to a 50 amp solar breaker, or if you will, a 9.6 kilowatt inverter, whereas the panel on the right that has 225 amp buses could accommodate almost twice as much solar. So we've had many situations where we'd show up to a build that was supposed to have been net zero or otherwise, zero energy building performance, where unfortunately service panels were installed that didn't have enough bus capacity. And in order to install a solar system of the size required to meet the project's energy targets, the service panel had to be ripped out and a new one installed. Of course, this is an extra cost that can totally be avoided in a new build if we think about this at the design stage. Okay, so that's an ouch. That's an example of painting yourself into a corner. Other considerations is we have to set aside space for a lockable disconnection point for the solar system between the utility and the home. We got to plan routing for solar electric cables. For example, the DC cables coming off an array have to be inside metal when they come inside the building. We have to plan for that in advance. If you're wanting to plan for hybrid inverters with storage, either for now or for the future, if you want to future-proof the house and make it solar and storage ready, you need to think about where the battery storage might be located and how big it might be, because there's limitations in code around those things. You've got to think about where the hybrid inverter will be located. It needs to be close to the battery storage system. And then most importantly, you'd want to think about how can we wire the house right up front. Even if you're not planning for battery backup now, it's not that hard to install an essential services subpanel and put all of your critical loads like refrigeration, freezers, communications, basic lighting and outlets into that subpanel right off the hop, so that later when you're adding a hybrid inverter and storage, you're not having to smash walls down and tear electrical circuits out to reroute them into a new panel. That might only cost a few $100s up front, and it could save thousands later. Again, if you're planning at the design stage, this is much less painful. So my message is, don't let solar and storage be an afterthought. You'll get much better results if you think about it ahead of time. So around the solar and storage concepts, I wanted to look at a case study of a home in Vancouver that was built by Arthur Lowe at Insightful Healthy Homes. Many of you may know him. A couple of years ago, he built a home to the Living Building Challenge standard in Vancouver, and we had the honor of helping him with solar PV and storage design, consulting, and installation. The home is fully electric. It's Living Building Challenge requires that we go beyond net zero to produce at least 105% of the home's annual electricity use. Energy storage is compulsory. It has to be designed to sustain essential loads backed up for a minimum of a 7-day grid outage. It uses rainwater collection to reduce domestic water supply reliance, and there's restrictions on allowable construction methods, and there's many more constraints that have to be met around sustainability and environmental impact. And Arthur and his team did a beautiful job of this project. And this is a little bit of what it looks like. This is the backyard of the home. And so not only is there PV on the flat rooftop, there's also PV on the backyard garden trellis. We needed the extra capacity to meet the energy production requirements. This is the electrical design of the inverter system. So we've got upper and lower, or if you will, east and west rooftop arrays, and then the trellis array. And we're using optimizer-based inverters to make the system very shade tolerant, because it's the site is somewhat compromised by shade trees. And then this is the second part of the electrical system. So we kept it down to a 200 amp service by using some load mitigation techniques, such as smart EV charger control. And you can see right at the design stage, we allocated an essential services panel for backup. There's a grid isolation means, which separates the local microgrid from the grid during an outage. And then we've got solar generation integrated along with hybrid inverters and storage in the form of Tesla Powerwalls. These are the two rooftop systems. It's a flat roof, and we had to use custom racking. It was all custom engineered because it had to be invisible from the road. And this is the microgrid with storage. So these are the solar inverters on the side of the building. 3 Tesla Powerwalls for hybrid inverters and storage. The service entrance disconnect is over here, and this is the grid isolator. This is what the equipment looks like. And then Arthur and his team enclose this in kind of an outdoor weatherproof electrical room closet, which is accessible only to authorized personnel. So as a call to action around achieving best electrification results, these are things we've talked about. And if you take away nothing else today, I would highly encourage you to think about these 5 points. Number 1, be mindful about how electrification will impact our service sizing. electrical service upgrades are expensive and they might not even be available. Sometimes classic service sizing calculations, such as the ones we've looked at, could trigger service upsizing that might not always be needed. And so it's worth digging more deeply. I believe projects like this deserve design stage due diligence around service demand mitigation. And it turns out that the electrical code provides a mitigation of load demand. There's provisions there, such as being able to reduce our peak demand using interlocking and smart load switches, and also demonstrated load techniques if it happens to be a retrofit. Lastly, electrification should be mindful of the possibility of solar and storage, either immediately or for the future. And those impacts, those both impact the electrical service design and distribution in the building very significantly, and they deserve to be considered together with the electrical service sizing and load management at the design stage. Don't let solar and storage be an afterthought. Okay, so that's all I have to say. I'd love to answer questions, and I hope you found some of this useful. And I'd love to connect with you offline if there's any ways we might be able to help you in the future.
And that was really awesome. We do have a couple questions. I have one, but before I ask that, Austin had a follow-up on his previous question. So he wanted to know if there's a requirement within the electrical code for there to be a safety factor on the panel. So if the calculations are showing 195 amp, that could be allowed, that could be above the safety factor. Let's say a safety factor of 20%. So the limit would be 160 amp.
Right. That's a great question, Austin. And that's something that also had confused me in the past. When I first started delving into electrical service sizing concerns a couple of years ago, I had mistakenly assumed that the service had to be derated. In other words, that a 100 amp service could only deliver 80 amps continuous, that a 200 amp service could only deliver 160 amp continuous. I was in fact wrong about that. And when I spoke to electrical colleagues in Technical Safety BC about it, they told me no. In fact, for calculation purposes, you can go right up to the nominal rating. So your service calculations for 100 amp service, you can go right up to 100 amps. If you go over 100, then you have to consider an upsize. Yeah. So great question, and one that I was certainly mistaken about myself, but I've been set straight.
Very good. Ben, I got a question for you around energy management and load sharing devices. So a lot of these are like, for lack of a better term, seem to be deemed approved for use with specific devices. So EV charging. Can you comment a little bit on sort of the industry discussions around that and use for like heat pumps and stuff?
Yeah, Ryan, that's a great question. Let me just pull up a slide that I think relates to that. I think this one here is the one, right? Rule 8-106, Part 11, specifically says that we can use smart load switches like this to enable or disable EV chargers based on measurement of the current coming into the service panel. About 8 months ago, I was on a Technical Safety BC training session where they were talking about how to use the demonstrated load method. And it was being delivered by two senior inspectors, both very experienced and really know their stuff. And the question was asked, what's so special about an EV charger? Why couldn't I use this to control my electric boost or my electric supplementary heat? Or why couldn't I use it to control a hot water tank or an electric sauna? And one of those experts said, I don't see any reason why. And the other one said, absolutely not. So So part of the problem is with code is that it's often viewed very prescriptively and viewed as though it's telling us what we can't do. And if we look at it more open-mindedly, there's places where it's telling us what we could do. And I think that particular question, whoever asked it, it's a fantastic one. In my view, there's nothing special about an EV charger. It's just another heavy electric load. And if we can use this technique with an EV charger, why shouldn't we be able to use it with another heavy electric load? And I think it'd be one of those things where, you know, depending on your electrical safety authority and who has jurisdiction and even individual inspectors, if you asked, you know, multiple people, you wouldn't get the same answer. Some would say yes, some would say no. I think it's an example of an opportunity where people that are, you know, revisiting revisions to Section 8 have an opportunity to clarify the intent here.
Right.
Yeah.
Okay, very, very good. That's very helpful. Any other folks out there before we move on to the electric utility?
There's a couple
Presentation?
questions in the chat.
Oh, there is some more. Oh, I must have
Yeah.
missed those. Oh, I
So
did. Good one. Okay.
do you want to, I'll let you facilitate.
Yeah, it doesn't matter, Sarah. Sure, I can go. Okay. Surinder, cost of having solar panel included, in Lower Mainland where it rains a lot. So are you asking for like ballpark estimates of design construction costs for various array sizes, Surinder? If I kind of, or are you asking specifically for a project you're working on, or
maybe if it's worth it.
It's
Maybe
worth
it's just
it, or
so general,
cost
like
wise where it rains a lot, and
Sure.
how does the cost compare to not having it versus having it?
That's a great question. Thank you. There's a metric that's used in the solar industry all around the world to measure and quantify how well solar works based on your location, you know, on the globe. And it's called insolation, or sometimes PV effectiveness. And what it measures or quantifies is the amount of energy in kilowatt hours that would be harvested annually by 1,000 watts worth of solar panels. So imagine 2 500-watt solar panels properly deployed. How much energy would those harvest in a year? Okay, so the BC average is somewhere around 1,000. The Vancouver area, Burnaby area, is somewhere around 1,020 to 1,030. In Kamloops, it's about 1,160. You might think, well, gee, you know, that number, what does it mean? Well, it doesn't mean much until we start comparing it to other parts of the world. So for many decades, Germany was the leader in solar adoption. And the PV effectiveness in Berlin, Germany is about 860. Okay, so in other words, the effectiveness of solar in the Lower Mainland of BC is at least 20%, maybe 25% better than the world's most aggressive adopter, or one of the world's most historically aggressive adopters of solar. So, you know, my question always is, well, how well do we want it to work? Like, it's true that it rains in Vancouver and that it's cloudy in Vancouver, but it's also sunny at times of the year. And what we're looking at is the long haul. We're looking at what happens over the course of the whole year, you know. So it's true that, you know, in the fall, late fall, winter, early spring, it might be wet and more cloudy, but there's months of the year where you produce more energy. So over the course of the whole year, solar actually works just fine in the Lower Mainland and Vancouver Island. areas. A bigger constraint is really if my panels are shaded, because not all locations are a good location. So if your home happens to be surrounded by, tall fir trees, and your roof is shaded all day long, it won't be a good solar site. So it might be true that your home in Vancouver is a poor site because it's surrounded by shade trees, but it's not accurate to say that solar doesn't work well in Vancouver. And particularly in the last 5 or 6 years, maybe 7 years, where the cost of solar has continued to drop and the cost of electricity has continued to rise. There's no longer a contest. Like the point where those lines cross, where it costs the same to buy energy from the sun as it does from the grid, those lines crossed back in 2017. And since then, it's been less expensive to generate some of your energy from the sun than to buy it from the grid. So there's a pretty decent business case. It's a decent investment, but it's not a license to print money. Again, there's due diligence involved to make sure that your site is going to work well. So I wouldn't hesitate to install solar in the Lower Mainland as long as you have a good site that's not shade compromised by mountains or trees or neighboring buildings. And around cost, I think a good number to use for budgeting, if you guessed somewhere around $2.80 a watt, which should be like, $14,000 for a 5 kilowatt system or $28,000 for a 10 kilowatt system, that'd be roughly in the ballpark.
Nice.
And you could count on that 10 kilowatt system, producing roughly 10,000 kilowatt hours a year, as long as your site was not shaded.
Okay, very good. That's awesome, Ben. I think you've
Thank you.
covered another question from Edward as well. We have a question from Rob, specifically around design strategies. So this one is what area should designers be using for rooftop solar panel array? And then what size of room or wall area is needed for solar panel storage inverter?
Yeah, those are great questions. I would say that in our part of the world here in BC, that you can make quite good use of any surfaces that are anywhere from east through to the south, through to the west. I would tend to shy away from anything that's more north than that, but it depends on your energy target. So like if you have a net zero goal and you don't have enough surface on your east, south, and west roofs, there are cases where we've used pieces of a north roof to get us there. But the best roof surfaces are going to be east, south, and west. And obviously south is the best, but you can be considerably off of south all the way to east or all the way to the west, and it can still work okay. Particularly if it's a low pitched roof. Like the steeper the roof, the better it'll perform, the more southerly it is. But for practical roof pitches, east, south, and west are all workable.
Oh yeah, he was actually asking about the square footage area of the roof too.
Square footage doesn't mean much at all. You have to be more concerned about having large continuous surfaces rather than chopped up multiple tiny surfaces with with lots of roof facets. It's way better to have larger surfaces all in one plane than a whole bunch of tiny surfaces in different planes. So just to say I've got, say 6,000 square feet of roof, that doesn't mean anything to a solar designer. You need to know how that's distributed. Is it all on one surface, or is it spread over 10 surfaces that are facing 10 directions? So my strategy or my advice there would be, if you want a roof design that'll be the best for solar, keep the surfaces to a minimum and make them as large as you can with as few disruptions as possible.
Okay. Mike Rugamer, nice to see you, Mike. I don't think you have a question to do, but he's just commenting that his off-grid cabin has had solar panels for 4 years now. Our batteries have 42.5 kVA. We're off the grid. Mike, I don't know if you want to unmute yourself and comment. I know your house is super impressive. So I don't know if you wanted to share some thoughts on your own solar design experience. Oh, we're not hearing you. Not hearing you, Mike. All right. Might get you next time.
I'd love to hear about Mike's project. Maybe Mike could give me a call later.
Yeah. Do you know Mike, Ben?
No, I've heard
You
it.
should meet Mike.
I've heard his name, but I've never had the pleasure of meeting him.
You guys need to meet. I'll make a connection here. And then Rob had a follow-up, but the city requires solar panel described on permit drawing, and the structural engineer needs to know the weight for the design of the structure. So I guess he's getting into the more detailed design piece here, Ben, about requirements with the city.
Yeah, for sure. So, not all municipal governments require permitting for solar. I'm assuming New West does, which is all fine. And that's even more reason to be considering these things at the design stage.
Yeah.
Because you will potentially need structural assurances, you'll potentially need stamped electrical drawings, a sign off on the attachment strategy, et cetera, as part of the permitting requirements. All the more reason to be looking at these carefully at the design stage.
Who's the who would you say in the provinces is the most evolved from a sort of like compliance and verification, municipal standpoint when it comes to the right
Well,
who's doing it really, really well? Not to
well, I don't want to embarrass anybody or call anybody up. Yeah, I would say that those that are doing it more stringently, would be lower mainland jurisdictions.
Yep, makes sense.
Yeah. Now, it sort of depends on what the motivation is. Like if we talk about an abundance of caution, versus wanting to promote these technologies and make their adoption safe.
Yeah.
And without putting up tremendous roadblocks, then the honest thing to say is we're not there yet. Because it's really left up to individual municipal governments and townships and regional districts to set their own criteria around permitting. And I can say there's some very large, significant cities in BC that don't require building permits for solar.
Right.
And as near as I can tell, that's gone fine because they've put into place some upfront due diligence, which has given them the comfort to go in that direction. So I think there's a lot of good work to do. There's opportunity for good work to be done here in BC for building authorities to start doing these things in a more consistent way, like in similar ways. That would really support both building authorities and solar providers in making this work better for everybody.
Yeah. That was sort of the root of my question, and I was just curious because, the space I operate in is in the mechanical side, and we've been with load calculations and sizing of heating and cooling equipment, we've been trying to evolve sort of industry practices and regulation just to be more consistent with the sizing of heat pumps and stuff, and patchwork is difficult to navigate. But anyways,
it's challenging for a lot of building authorities because the technology is changing so fast. It's hard to keep up, and I can understand that people in those decision-making positions could be uneasy about what they're working with, and so there's a lot of good work to be done to help everybody here.
Yeah. Okay. I think we're pretty much at time, unless there's any other last minute questions. If not, we'll shift gears to
I don't know if Ben answered this. If I missed it, I'm sorry. What size room or wall area is needed for a solar panel storage inverter? Was that already answered? I think it was asked.
I think I skipped past that. Well, it depends. It depends very much on the amount of storage that that is required. So I don't want to be endorsing necessarily Tesla Powerwalls as the only product that can do this, but as an example, this is a really good example here. Each of these hybrid storage units, I believe, is roughly 12 kilowatt hours of usable storage, and they're approximately 3 feet wide, about 40 inches tall, and about, I think, 10 inches deep. So what we're seeing here is approximately 10 feet of wall space, but these guys can also be stacked, like you can stack them one in front of the other. So, and then there's other options as well. I think the thing to say here would be, if you're wanting to put storage, against a wall or in a room, there's quite stringent guidelines in electrical code around how big storage can be if it's going to be inside the building, and the room it's in has to have a particular fire rating. And in some cases, builders opt to put this hardware in a garage so that it's not inside the building envelope. So you really need to consult with a solar and storage provider to get good answers. And it will all start with the question, how much energy storage do I need to back up loads, during an outage? And so it's hard to answer the question without having the answer to that first one, how much storage is needed.
Perfect.
Yeah.
Okay. Sounds good. All right. Well, Ben, thank you so much. That was an awesome presentation. Good discussion. Really appreciate you making time to present. And maybe now we'll transition to Mr. Mark's presentation from the electric utility.
Okay. Thank you, Ryan. I think, Sue, you had the slides. Okay. Yeah, there we go. Okay, perfect. Yeah, we'll go into the first slide there. So yeah, just a quick introduction. So Mark Rudishauser, I'm the Deputy Director of Electrical Services here at the city. So electrical services, we're part of the climate, energy and climate action department. So I look after the electrical side of that. I've been with the city about 15 years here, so I think I have a decent idea of how the city kind of runs. And then kind of quick introduction here to our department. In the electrical department here, we have 3 divisions. Electrical design and planning is the in-house engineering project management side. So for all developers, when you're looking for new connections, you'll be interacting kind of with our team there. And then electrical operations is the power line technicians and utility operations. So these are the crews that maintain and construct the system and do all the work you see out there, do new service connections, that type of thing. And then we also have electrical services under us. And this team is the electricians who maintain streetlights, traffic signals, city facilities, and do a lot of the internal work for the city. And then we actually also have it included in the slide here, but we also have BridgeNet, which is a dark fiber utility that's under us as well, that operates in the city. Okay, next slide. Perfect. So kind of this, again, this presentation is kind of pretty high level. I don't have all the nice drawings and graphics that Ben had. That was really, really good, but this is kind of going to be more of a quick interview. So feel free to jump in if you have a question, and there'll be lots of time at the end for questions as well. So, okay, quick introduction to the City of New West electrical extension policy as per our bylaws. So again, here's some pretty boring clips here straight from the bylaw. Important things to know here for electrical extensions. So the first one, extension, the definition here is any addition or upgrade to the city's electrical distribution system required for a new service or a service upgrade. So really that means any change to your electrical service that triggers any work from the utility, that's considered an extension. And now in the terms and conditions here, we've got important thing to know about the extension is that the city may, at its sole discretion, either refuse to provide the extension or provide the extension subject to the following conditions. And that's that the applicant pays 100% of the costs incurred by the city in providing the extension. And so the applicant has to pay the city upfront before doing that work. Now, again, in practice, we don't refuse services very often. I think that there may be some special circumstances. There are a few areas in the city that are actually served by BC Hydro, so that could be one of the exceptions. But typically, we'll work with you to get the extension that you need. And then another important consideration here is an amendment we had to the bylaw in 2007. And that states that all multifamily, commercial, mixed use, and newly constructed single family and duplex buildings shall be designed for an underground service. So that's to say that every single new service in the city has to be underground. Every service upgrade has to be underground as well. There's one exception to that for 200 amp overhead service upgrades for houses, but effectively anything new has to be underground. So just keep that in mind, because the costs will be higher than for an overhead service. Okay. So some typical extension types here. So a single family house, this is where we actually have standard charges in our bylaw. So currently for a new single family house, the cost is $9,371. Every year, this is subject to changing, but that's the current cost. And that's actually for a service up to 400 amps. So again, typically we'll see a lot of new houses have laneway suites and basements. So that extension cost covers you whether you're building something 200 or with multiple meters up to 400 amps. It's the same extension cost. These extensions are usually single phase, 120, 240 volts. Something to keep in mind, in some cases, we'll need to install an LPT, a low profile transformer. Often we won't have to do that. And whether we do have to do that work or not, we're not charging the single family dwelling for that. It's still the fixed charge. Moving on to subdivisions, townhomes, small commercial buildings. This is where, your service extension is actually at cost. We don't have set fixed charges for that. So the extension cost is as estimated by the city. So we'll take a look at it. We'll need, all the electrical drawings, all the details. We'll determine what has to be done for that extension, and then provide you that cost. And then you have to pay up front to get that work done. So these are typically secondary services, 120, 240 single phase or 120, 208 volt 3-phase. Keep in mind these secondary services, we don't provide 600 volt services for commercial services. You're limited to 120, 208. And so these type of extensions, they'll often need a PMT, so it's a 3-phase pad mount transformer or a single phase pad mount transformer. And again, depending on the design and the space there, they'll often need to be on the developed property. So keep that in mind. You'll often have to provide that space for subdivisions and townhomes. And then moving on to the larger services. So these are multi-residential, commercial, industrial, larger buildings where they have their own private transformer. So the city won't provide transformers for those large services. They need to be provided by the developer on site, and they need to be rated at 12 kV and 25 kV for the future. And so these are, so the transformer will be called a unit substation for these type of developments. And again, the developer has to build that all to code and own that infrastructure. So that's something a little bit different. Next slide. Okay, so some quick comparisons between our extension policy and hydro. Some similarities. The extension costs are estimated by the utility. So hydro does follow the same process. They'll take a look at all your submissions, see what work they have to do, and then estimate the cost for that. LPTs, PMTs are often required as part of the development. Again, very similar. We typically follow BC Hydro standards with a few small deviations, but that's going to look very similar to the BC Hydro area. And so, like I said, the process is comparable. We'll start working on the design once we have all the electrical details and determine what we have to do there. We follow BC Hydro standards. Again, small deviations, but typically rule of thumb, if you're following BC Hydro standards, you shouldn't really have any issues here. And again, always encourage you to speak to our team and ask questions if you have any questions there. So some key differences. The city does not provide a contribution credit to help offset the extension costs. So I don't know how many of you have been following BC Hydro's extension policy, but they actually recently updated it. They have been providing a credit for quite some time, but they've now updated their policy to up that credit. So effectively lowering costs for development. We don't provide that credit. And again, no plans in the future to do that, but you know, these things are always subject to review. But at this time, we don't provide any credits to help offset costs. Another difference is, our mandatory underground extensions. So even for single family dwellings, BC Hydro typically won't require that unless it's a new subdivision. But here we do require everybody to put in that underground service. And then, so City of New West here, we actually have standard charges for single family services up to 400 amps. That's a little bit different than Hydro, where they'll typically determine their costs for that type of work. And then I alluded to it a little bit earlier, but BC Hydro provides larger secondary services for development. So their transformers will actually go up to 1500 kVA. In City of New West here, we won't go past 500 kVA as a transformer that we would provide. So that's something that could, it could provide enough power for a townhome development. But usually when you get larger, if it's a very large townhome development or multi-unit, the developer is going to have to go to their own unit substation for that type of service. Okay. Okay, so just some quick examples here. Going into a typical single family home extension we see in New West here. Usually we'll see 3 units, like I said, main suite, basement suite, laneway house. This is almost the standard for new homes. They'll usually request, again, 3 electrical meters in a multi-positioned meter base rated up to 400 amps. Usually the calculated code we see is between 200 and 360 amps. So as Ben was alluding to here and spoke in pretty good detail about, if your code load is over 200 amps, that triggers you having to go to the next size, and that's often 400 amps. So again, we will allow that here for these underground services, because we know that with these type of developments with multiple suites, it's very hard to keep it under 200 amps. And we provide that service up to 400 amps. So just some quick facts on that. So underground service extension, it's usually a service box. Usually what it looks like on the city property is a service box connected to a pole or connected to an LPT if we have to put that out there. Now that's all the work that's out on city property. That's what we collect the fees to construct that side of it. And then everything on private property obviously is the developer's responsibility there. So another thing to keep in mind here, the underground telecommunications, whether you go with TELUS or Shaw or potentially another provider, but those are usually the 2 we have here in New West, that service is also required to go underground. So the process we have here is usually once we have the submission from the developer, we'll create our drawing that gets passed along to TELUS or Shaw, and they create their drawing in a joint trench, and we jointly build that to help save on charges there. Like we spoke about, our standard charge is $9,371. Thing to keep in mind here is that you have to pay TELUS or Shaw separately for that, and they don't have fixed charges for these developments. So again, they're going to be kind of like Hydro. They'll determine what their actual cost is and charge you, the developer, the actual costs. And as we've seen recently, with inflation and cost escalation, I don't think we've ever seen their charges be less than ours. They're almost across the board higher. So keep that in mind. And then another point here is that the service cable from the city service box to the meter base will be provided and owned by the developer there. So that's a little bit different than Hydro. With Hydro, they will own that service cable and they can size it as they wish, because again, utilities are not subject to code here. But in US, since the homeowner or developer owns that cable, it does have to be sized to code. So again, just a detail that keep that in mind. And next slide. Okay. A duplex extension, very similar. You'll often see 4 units, 2 main suite, 2 basement suite. We're starting to see a lot of those. 4 meters in a multi-position meter base. Same, usually up to 400 amps can do the trick there for that type of development. You know, the extension you're going to see in the city is very, very similar. Usually a service box, maybe an LPT. TELUS and Shaw has to be underground, and same thing. Probably the only difference, the main difference here is that if the duplex is actually 2 separate properties, or it's subdivided, you will have 2 separate properties 2 separate services from the city. It won't be one. But if it is one lot, a stratified lot, then it will be just one service to that development. Okay, and a townhome extension. So in this example, we've picked 10 units, but we've seen anything from, I'd say, six units up to 20, 30, 40, and 50, and get into the bigger developments here. But in a typical 10-unit townhome development, again, you're seeing separate meters for every unit. You'll sometimes see an additional common meter if you have some common loads. Usually the load fits in between 400 and 800 amps for that size. That's usually what we've seen. Now, on the utility extension side, that will trigger an LPT or a PMT or a 3-phase PMT and conduits installed in the frontage to help underground the power lines in the future. Now, yeah, keep in mind that LPT or PMT is on private property. That's, again, the default is that you'll have to provide that space to accommodate the PMT. Undergrounding TELUS and Shaw, same as all the other ones, that's required as well. And the extension costs are going to be estimated by the city. So again, no fixed charges here. We'll have to look at all these individually, determine what it costs us, and effectively send you the bill before we construct that. Okay, and then quickly here, some other standard charges we have. So like I said, the service upgrade, the only exception here to the underground rule, we will allow overhead service upgrades. So these are for existing homes. If you have a 60 or 100 amp service, we'll allow you to go up to 200 amps and keep that overhead service. And as you can see, the standard charge for that is $933. So obviously that keeps costs down, but that's only available for existing homes. Anything new does have to be constructed underground, and there are a lot higher costs there. Disconnection and reconnection. So these fees are typically for maintenance or anything you're doing, in your home. If you have to disconnect your service and you're doing some maintenance or electrical work that isn't triggering an upgrade, those are the standard charges. So $600 in work hours and $870 any other time. And then temporary service connection. So this is typically, you're building a home, you need temporary power to get construction power on site. So we have standard charges for that as well. And that's about $1,000 for the underground and $960 for overhead. Okay. So yeah, net metering. So quickly here, Ben spoke about it here. We do have a net metering program. It was approved by council in 2016, and it allows systems up to 50 kilowatts to be connected to the city's distribution grid. It requires an interconnection agreement with the city, and that's certifying that it meets the CSA standards and all other requirements. And again, it is very similar to BC Hydro. There aren't really significant differences here. So usually the process is, as with an extension, we'll ask for all your drawings. We need to see those specifications. There's a declaration that the agreement has a declaration that it meets these standards, and that it's good to connect. Now, something to keep in mind here, for the energy generated, it's credited back to your account. So if you're pushing anything back to the grid, it's credited back to your account at the normal rate. So we don't have special rates at this time for the net metered energy. It's just credited back at the same rate that you're paying for power. Now, if more energy is generated than consumed at the end, it usually will be paid back. I think we have provisions where if it's a small amount, we may not pay that back. We'll keep that credited, but if it is a bigger amount, that'll be paid back. So again, the process is quite similar to BC Hydro, and the requirements are quite similar as well. And yeah, there's more information on the website. And okay, yeah, just maybe one more thing. I didn't have a slide, but touching on the AMI project that Ben spoke about as well, just maybe a quick update on that. We are, I believe, I'm actually missing the AMI meeting right now, but I believe we're at about 80% complete with the residential deployment. So we're getting pretty close. We're getting pretty close with all the residential AMI meters that'll be out there in the city. The commercial meters will likely we'll keep working on that until the end of the year. So we won't be finished that right away, but the residential, you'll start seeing AMI meters quite soon. Now, what that means in terms of data, the meters are rated to provide hourly readings. So that's information that we have right now. What I will say is that we don't have this will be a separate project once deployment's completed, but we don't have the customer portal side of things ready. So Ben showed what you can get with BC Hydro. That's still a separate project with the city. We don't know exactly when we'll have that ready to roll out, but it won't be until AMI is fully complete, and then we'll get onto that project. So that's all to say that the data will exist. We'll have much better data than today. And there'll be ways of accessing that. We'll have to work internally on what the process is, but the data will start to be a lot better than our current data, which is really just one reading every 2 months, and it's just your build use. So we recognize that we're working with a lot of developers and stratas looking for that information, and the information we're able to provide right now doesn't really help a lot. So again, right now the best way is still to use a data logger right now if you need really good information at your site. But with AMI, we're definitely getting there where we'll have better data soon available. So yeah, so I think that's all I have here for the kind of high level overview. And yeah, I'm happy to take any questions on any of these topics or anything else that comes to mind. So
Good stuff, Mark. Thank you for that. There was one question for Ben, but we won't get to that one until we've covered any that are here for yourself. And actually, I'm not seeing any in the chat. Everybody's quiet on the city stuff, Mark. You might be getting off easy here.
Oh, okay. Yeah, I know I went through that really quickly, so maybe it's still kind of processing. But yeah, any questions? I guess again, contact info is there. So what I'll say as well is definitely check our website for any questions on on policy. Feel free to email or phone. That's our general line there. But you should be able to get anyone on our team here who's very knowledgeable on all our policies and all our design details. So yeah, we always encourage everybody to contact us early. I know usually for developers the first point of contact is planning and the permitting process, but definitely contact the electrical department as early as possible if there's any questions on your electrical service, because it can certainly help answer questions and steer you in the right direction early on. That definitely can provide a benefit there. So
awesome. So thanks, Mark. Appreciate your time. That was fantastic. Ben, did you want to cover off any recommended alternative battery options other than the aforementioned Tesla brand?
Well, can you hear me, Ryan?
Yeah, you're good.
Yeah. I mean, I don't want to suggest any of these brands are any better than others, but there is a plethora. One thing to be aware of is the Tesla Powerwall product is actually not just a storage battery, it's also a hybrid inverter. And the more recent iterations of the Tesla Powerwall actually allow it to act as a solar inverter as well. So it's kind of an all-in-one solution. There's not a lot of other products out there that integrate all three. But an example of an inverter technology that gets you part of the way there would be a product like SolArc, which is a solar inverter and a hybrid inverter that can work with or without batteries. And then you can couple an inverter of that type with battery storage from Pites. Other ones might be Discover. There's a variety of others, like, so, and no one is better. I think it's my advice would be, do some research and talk to a trusted solar and storage provider. There's multiple options, and they all have advantages and disadvantages. I mean, one advantage of the Tesla Powerwall is it's very sleek, and and it has everything in one box. But there's also disadvantages to that. It makes it somewhat less flexible and difficult to maintain and repair. So yeah, if somebody wanted to talk to me offline about that, I could give better advice.
Sure.
Yeah.
Perfect. Thanks, Ben.
I did notice someone looks like Kirsten Reiser. Oh, it just happens to be the daughter of a very good friend of mine that I used to teach with at TRU. Kirsten is asking about access to the slide deck. That's going to be available, isn't it, Ryan, for all the participants? Yeah.
Well, we send out a follow-up email to everybody with the link, and then it's posted on our website. So
yeah,
we've got stuff available.
Okay, excellent.
All right. I think we're just finishing up with the Sarah City stuff, little program promo from Energy Save New West, and then we're call her a day. So maybe Sue, back to is Sue sharing on your side?
There's no slides.
Okay.
Yeah, for me, it's just a verbal update, pretty quick. So yeah, for those of you I haven't met, my name's Sarah Maleska. I'm the Community Energy and Emissions Specialist at the city. I've worked here for just over a year now, and I'm kind of like the step code person, retrofits as well. And I just have just a couple kind of quick reminders. So just for step code, remind you all, I'll put the link in the chat of what step we're currently at. There was an update on January 1st of this year. So for Part 9 buildings, which I think is the majority of our attendees, we're at step 5 of the energy step code with EL2 of the zero carbon step code, or you can do step 4 of the energy step code with EL4 of the zero carbon step code. So that was as of January 1st of this year. And then just a reminder, in I guess a year and a half now, January 1st, 2027, we'll be moving to the highest step. So step 5 EL4. And then I just wanted to mention this project that I'm working on. It's called Charged and Ready. So basically now that New West has had its EV ready requirements in for residential buildings since about 2019, we're kind of checking up with those buildings and folks that live in those buildings to see how it's going to live in a place that's EV ready. This is a project that's funded by BC Hydro, and we're partnering with City of Nanaimo, Victoria, Township of Langley, Richmond, Vancouver, and UBC to survey select buildings in our community that, according to our building permit data, we believe were built to be EV ready. So there is a resident survey. So if you happen to be a resident in New West and live in an EV ready building, we'd love your input. Or if you know of someone that lives in an EV ready building in New West, and also a building professional survey. So I'm going to put both links in the chat. I think it's open until June 22nd, so about 4 more days. And yeah, kind of the goal of this project is to see how EV ready requirements are working in the wild. We've heard some rumors in other municipalities that sometimes, even though the spot is EV ready, like that doesn't mean the charger's installed. And so folks have been running into issues with Stratas charging kind of a lot of money to install that charger or putting up other kind of roadblocks. There's been some rumors of the conduit, like the actual electrical infrastructure not being installed quite correctly. So we're just trying to figure out, okay, we have this policy for EV ready buildings and how is it going? So yeah, please, the links are in the chat. If you know anyone that lives in an EV ready building in New West or those other communities that I named, please forward the survey to them. Thank you.
Awesome. Thanks, Sarah. Henry is asking, does New West still provide energy code design? Are you asking, do we still support some projects with EA services and assistance with zero and energy step code requirements? Is that what you're looking at, Henry? Yes, we do. We still have that service available for select projects if we haven't worked with you, and if you're doing step code 5, we have some support services there. You can reach out to through our website as always, or email me or the program. We can help you out. Yeah, we just have a couple updates to close out. One is just a project, our latest case study. This one started before the new requirements. So 819 Milton Street. This was our first multiplex. So it was a 4-unit house, completed step code level 3, very good energy performance, 40% better than code. It was the first project that we've done with a ground source heat pump. We're still compiling some of the source information at as built, but we'll be listing this up on our website and talking more about this project in our newsletter and stuff, and really good air tightness that we've been getting with the projects that we've supported, which is great. So you'll see more of that, and then yeah, similar call to action. So we announced this pilot earlier this year, where we would like to support a few new home Part 9 construction projects with getting some embodied carbon analysis. So some technical consulting services on the embodied carbon of the materials that are being used for construction. So we're de-risking and de-costing this for builders to try to familiarize ourselves as well as yourself with what does the material embodied carbon look like for projects being built in New Westminster. So similar to 10 years ago when we were chatting with you folks about, hey, familiarize you with EAs, and we'll make services available. This is a similar call to action. We want to do a few projects here with some builders to better understand and support in this space. So if you have an initiative coming up and you've worked with us, that's great. We'd love to hear from you. And if you haven't worked with us before, City and Energy Save New West, we'd love to hear from you too, and chat about supporting with this piece of work. So same thing, reach out to us via online or yeah, there you go. And Sarah even posted it. Thank you, Sarah. How to get a hold of us. So, and with that, I think we are all done with content. So unless there's any remaining questions, so similar closing thoughts, I guess, is we will issue out the builder credits for this to folks. So you'll get an email from the program that you can use for the BC housing piece. And then as well as we'll be posting on our website a blog post with the presentation decks in PDF and then a recording of the session as well. So stay tuned for those. And then as always, if you've got some ideas, I believe this session actually came from a builder or I'm pretty sure around electrical design strategies. Please send them to us. We like to find new topics and new keynote speakers to address things that are of curiosity and interest for those building houses in New West. I don't know if you, Sarah, if you had any closing words or.
Not really, just put it in the chat. Thanks everyone for coming. Great questions. And I guess, yeah, we'll see you in the fall.
See everybody soon. Bye now.
Thank you.
Bye.